Okay, so today we're going to talk about Blackboard assignment number 6, which is really just our lesson 2 discussing multiplication and division of complex numbers. So to begin, we're going to look at a couple lesson 2 intro examples that are going to get us started into some more deep conversations about these complex numbers. So to remember back to lesson 1, we talked about the imaginary unit I, and that it was equal to the value, the square root of -1. We also talked about in lesson 1, the imaginary unit I, if we square it, we get the real value, -1. So I is not a variable, it's actually a value, but it has a lot of properties, or the properties that it does have, we can use it and treat it like a variable when we're adding, subtracting, multiplying, and dividing. So in this first example, we have -I times the quantity 9 minus 6I. So if we take these two complex numbers, these two imaginary numbers, and we multiply them, we're going to treat I as a variable, but we know that I actually has a value. So -I times 9 gives me -9I, and -I times -6I gives us a positive 6I squared. And at this point, we know that I squared has a real number value. So we can plug -1 into I squared and simplify. So we can get -I plus 6 times the quantity -1. When we do that, we can just crunch those numbers, and we're going to write our real number piece of this complex number first and the imaginary part second. So 6 times -1 is -6 minus 9I. So -6 minus 9I is the new complex number we get when we take -I times the quantity 9 minus 6I. In number 2, we have two complex numbers here being multiplied. We have 2 minus I times the quantity 5 minus 2I. And it's going to act and be treated very similar to if we had variables here and we FOILed. So in this case, we're going to FOIL. So F means first, O means outer, I means inner, L means last. So we're going to take those terms and multiply them. So number 2, we're going to start by taking 2 times 5, which is 10. 2 times -2I, which is -4I. -I times 5, which is a -5I. And -I times -2I, which is a positive 2I squared. From here, we can take our like terms and combine them. So we get 10 minus 9I plus 2, and we can plug in again, just like we did in example 1, -1 for I squared. We then get 10 minus 9I minus 2. Combine our like terms one more time. And we're going to write that whole number piece out in front. So 10 minus 2 gives us 8. Minus 9I is our imaginary part. And that is our new complex number when we take the two complex numbers, 2 minus I times the complex number 5 minus 2I. In number 3, we have 4 plus 3I squared. So in this case, we can expand to get 4 plus 3I times the quantity 4 plus 3I. And again, we're looking at a very similar problem as we did in example 2. So we can FOIL. So if we go with our F, means our first two terms, which is 16, 4 times 4. Our outer two terms, which is 4 times positive 3I, gives us a positive 12I. Our inner two terms is 3I times 4I, which is another 12I. And then 3I times 3I is a positive 9I squared. Combine our like terms. We'll get 16 plus 24I plus 9. And we can plug in again -1 in for I squared. So we get 16 plus 24I minus 9 which of course if we combine our like terms again, we're going to get 7 plus 24i as our final complex number. So to multiply complex numbers, we can use the distributive property or the FOIL method just as you would when you're multiplying real numbers or algebraic expressions. Some of the other properties that also hold true for complex numbers include the associative property and the commutative property. So let's look at a couple more examples as we push through to get a better understanding or a little bit more practice with these multiplying complex numbers. So let's look at a few more. So in letter A we have 5i, which is a pure imaginary number, times the quantity or the complex number -2 plus I. -2 is our real number part for this complex number. The I is your imaginary part. So if we multiply through, just like we did in our lesson 2 intro examples, we're going to treat I as a variable, but we know that it actually has a value. So at the end, we have to make sure we double check those I squares and make sure that we plug in -1 before we end with our final answer. So 5i times -2 gives me -10i. 5i times I gives me a positive 5i squared. I squared I know is equal to -1. So I can plug -1 in for I squared. And then, of course, we're going to write our real number term out in front and then our imaginary part second. So we're going to get -5 minus 10i as our final complex number answer. Letter B, we're going to use our FOIL method here. So our first, outer, inner, last, our first two terms when we multiply them, 7 times -1 is a -7. Our outer two terms, 7 times positive 2i is a positive 14i. Inner is -4i times -1, which is a positive 4i. And -4i times a positive 2i gives us a -8i squared. Combine our like terms, we have -7 plus 18i minus 8. And of course, -1 gets substituted in for I squared. We combine our like terms one more time. This actually gives us a positive 8. So positive 8 minus 7 gives us 1 plus 18i. In letter C, we have another situation just like we did with lesson 2, intro example number 3. We're going to expand this first, then we're going to use our FOIL method to complete it. So we get 10 minus 7i times 10 minus 7i. We're going to FOIL one more time. So first terms multiply gives us 100. Outer two terms gives us -70i. Inner two terms gives us another 70i. Outer terms gives us a positive 49i squared. Combine our like terms, we get 100 minus 140i plus 49 times -1. -1 gets substituted in for I squared. -49 plus 100 gives us a final complex number of 51 minus 140i. And last but not least, we have letter D. And in letter D, we have the complex number 6 plus 3i times the complex number 6 minus 3i. So they're pretty much the exact same complex number, except one has a plus in the middle and the other one has a minus. So if we FOIL these two complex numbers, 6 times 6 gives us 36. If we go to our outer two terms, 6 times -3i is -18i. Inner two terms is a positive 18i. And then our outer two terms is a -9i squared. At this point, we combine our two like terms And what you'll notice is the negative 18i and the positive 18i cancel out. So we get 36 minus 9, and we substitute negative 1 back into I squared. Negative 9 times negative 1 gives us a positive 9. So we actually get 36 plus 9, and we get 45 as our final answer. So let's focus on example 1D for a moment. That's the one we just got as a 45 as our final answer. So let's focus on this expression for an extra minute. So what do we notice about this expression? Well, the first thing that we notice is that 6 plus 3i and 6 minus 3i are in a certain form. And the form that they're in is, we're going to call it a plus bi. That was our general complex number that we talked about yesterday. And the form a minus bi. And I'm going to underscore both of these because both of these combined are what we call complex conjugates. Complex conjugates. And the product, which means multiplication, the product of complex conjugates is always a real number. Always a real number. And that happens because we have the exact same values in for A, the exact same values in for BI, but the difference is one is positive and one is negative. And if you remember, if I had something like x minus 2 times x plus 2, that middle term is always going to fall out. And because that middle term tends to be our imaginary number, that's going to go away and we're going to end up with a real number. And we can use complex conjugates to write the quotient of two complex numbers in standard form. Quotient means division. So if we have a situation where we're now dividing complex numbers, those complex conjugates are now going to come in handy. So let's talk about, or actually go through one example dealing with these complex conjugates. So we're going to look at example 2, dividing complex numbers. This is the last example that we're going to do for today. And then the last two problems at the very end are going to be for you to work on. Okay, so let's look at this quotient. We have 5 plus 3i divided by 1 minus 2i. Okay, so the first thing we're going to do, and I'm going to write these steps over in the corner because they might be helpful as we continue working with complex numbers. The first thing we're going to do is we're going to start by multiplying the number, or the numerator and denominator, by the complex conjugate of the denominator. So we're going to start by multiplying the numerator and your denominator by the complex conjugate of your original denominator. Okay, so that's the first step. So I'm going to go back over here to my original quotient, which is 5 plus 3i, all divided by 1 minus 2i. So my first step has us finding the complex conjugate. That's the first thing that we need to find. So in my denominator, I have 1 minus 2i. Okay, so my complex conjugate of my denominator, 1 minus 2i, is going to be 1 plus 2i. The real number part stays the same. The imaginary part stays the same. The only thing that changes for complex conjugates is that the plus changes to minus or the minus changes to plus. And once we find our complex conjugate, we are then going to multiply our quotient by that complex conjugate 1 minus 2i, or 1 plus 2i, I'm sorry, that's your complex conjugate, top and bottom. So the complex conjugate of your denominator, we're going to find it by switching the negative to a positive, the minus to a plus, and we're going to multiply the bottom by the complex conjugate and the numerator by the complex conjugate. Once we do this, we are then going to FOIL the top terms and then FOIL the bottom terms, because we can't leave our complex number with an imaginary number in the denominator. So let's do this first. We're going to focus on the denominator. So let's FOIL these two numbers. So we get 1 times 1, which is obviously 1. Outer is going to be 1 times positive 2i, which is plus 2i. Negative 2i times a positive 1 is minus 2i. And negative 2i times positive 2i is a negative 4i squared. Because they are complex conjugates, our middle terms, which are the i's, cancel out, and we're left with 1 minus 4. We're going to substitute in negative 1 and for I squared, which gives us a total of negative 4 times negative 1 gives us a positive 4. Positive 4 plus 1 gives us 5 in our denominator. So we're going to hold on to that for one more second. In the numerator, we're now going to FOIL our numerator. So 5 times 1 gives us 5. Outer 5 times 2i gives us a positive 10i. Inner gives us 3i times 1, which is a positive 3i. And 3i times 2i gives us positive 6i squared. If I crunch these numbers together and combine our like terms, I'm going to get 5 plus 13i plus 6. And of course, we can substitute in negative 1 for I squared. So if I rewrite this, I get 5 plus 13i minus 6. And we all know that negative 6 plus 5 is going to give us a negative 1. So we get negative 1 plus 13i for our numerator. So I'm going to use a different color pen right now because I know there's a lot of writing going on your paper. So at this point, what we're going to do is we're going to take our new numerator, which is negative 1 plus 13i. That's what we get when we FOIL our two numerator or top complex numbers, divided by our denominator. Now when we FOIL these two together, we get 5. And we get negative 1 plus 13i. So if we separate this, one more step, we can actually separate this into a real number part and an imaginary part, so that negative 1 over 5 becomes our real number part, plus 13i over 5, or 13 over 5i. Doesn't really matter how you call that or how you state that, but you now have a real number part and an imaginary part, and this is your final complex answer, your number answer, that you got when you took two complex numbers and divided them from our first example. So that is your final answer. So at this point, we got through Blackboard assignment number 6. So why don't you work on a couple of these extra problems. We have A through D that is given to you on your worksheet. See how far you can get with all 4 of them, and the next time we all get together for class, we'll go over any of the questions that you may have and make sure that you guys have the right answers down.